Hey everyone, and welcome. Today we're going to jump into a really foundational idea in physics, vector resolution. This is the secret sauce for taking things like forces or velocities and breaking them down into simple parts. It's a skill that makes even the toughest problems way, way easier to handle.
So here's the game plan. We'll kick things off with what vector resolution even is, then get into the math for breaking down and rebuilding vectors. After that, we'll work through a practical example, chat about something called unit vectors, and wrap it all up with the key formulas you need to know. Sound good? Let's get started. All right, first things first. What is vector resolution? Well, you can think of it as a strategy, really. It's all about taking a vector that's pointing in some weird, awkward direction and splitting it into pieces that are just, easier to manage. This makes all our math so much simpler.
Just imagine you've got a force pulling on something at, say, a 30-degree angle. Now, dealing with that angle directly can be a pain, but what if we could break that one force down into two separate forces, one that pulls straight across, horizontally, and another that pulls straight up, vertically? Suddenly, things get a whole lot easier to work with.
And these simpler pieces, we've got a name for them. They're called the components of the original vector. They're kind of like the fundamental building blocks. If you put them back together, you get the exact same original vector back. Pretty neat, right? Now, you could split a vector into components pointing in any old direction, but that wouldn't be very helpful. The really useful way, the way we almost always do it, is to make the components perpendicular to each other, at a perfect 90-degree angle. We call these rectangular components. And here's the magic part. The horizontal part and the vertical part don't interfere with each other at all. This is a game changer for solving physics problems. Okay, let's get to the main event. How do we actually find these components? This is where that trigonometry you learned in high school becomes your absolute best friend in physics. Don't worry, it's simpler than you think. So picture a simple XY graph. We've got a vector, let's call it vector A, just sitting there. It starts at the origin and points out at some angle which we'll call theta from the horizontal x-axis. Our mission is to figure out how much of that vector lies along the x-axis and how much lies along the y-axis. You can almost think of it as finding the vector's shadow on each axis. Okay, so if you look at the tip of our vector and drop a line straight down to the x-axis, boom, we've just made a perfect right-angled triangle. And that bottom side of the triangle, that's our horizontal component, AX. And you can see it's the side that's adjacent, or right next to our angle theta. Now, think back to your trig. Which function deals with the adjacent side and the hypotenuse? That's right, it's cosine. So the cosine of our angle theta is just the adjacent side, AX, divided by the hypotenuse, which is the length of our original vector A. And if we just do a tiny bit of algebra and rearrange that, we get our first super important formula. The horizontal component, AX, is just the vector's total length, A, times the cosine of the angle. That's it. Just remember this. Horizontal component, think cosine. Okay, that was the horizontal part. Now what about the vertical part? It's pretty much the same idea, that vertical side we drew to make our triangle. That's the vertical component, A, and notice how it's the side that's opposite our angle theta. So which trig function connects the opposite side and the hypotenuse? That would be sine. So the sine of our angle theta is equal to the opposite side, AY, divided by the hypotenuse A. And again, just rearrange that equation and we get our second key formula. The vertical component, AY, is just the vector's magnitude, A, times the sine of the angle. See the pattern? Horizontal is cosine, vertical is sine. That's the key right there. Awesome. So now you know how to split a vector apart. But what if we need to go the other way? What if someone gives you the components, the horizontal and vertical pieces, and asks you to rebuild the original vector? How would we do that? So let's say I tell you the value of AX and AY. How can you figure out the length or the magnitude of the original vector A? Go ahead and look back at that right-angled triangle we made. The answer's hiding right there.
You got it. It's just the Pythagorean theorem, right? A squared plus B squared equals C squared. In our case, AX squared plus AY squared equals AZ squared. So to find A, you just take the square root of AX squared plus AY squared. Simple as that. All right, so we've got the length, but that's only half the story for a vector, isn't it? We still need its direction. How do we find that original angle, theta, if all we know are the components AX and AY? Well, we need another trig function. Which one uses the opposite side, AY, and the adjacent side, AX? That's tangent. So the tangent of theta is AY divided by AX. To get the angle itself, we just use the inverse tangent function on our calculator. So theta is the inverse tangent of AY over AX.
Okay, enough theory. Theory's great, but let's see where the rubber meets the road. We're going to apply this to an actual problem, because that's when this stops being just math and starts becoming a really powerful tool for physics.
So here's a pretty standard problem you might see. Someone tells you that the horizontal part of a force is 20 newtons, and they also tell you that the force is acting at an angle of 30 degrees with the horizontal. The big question is, what's the total force?
Okay, what's the first thing we do with any physics problem? We write down what we know. It's the best habit to get into. So we've got the horizontal component, let's call it Fx, that's 20 newtons, and we've got our angle, theta, which is 30 degrees. Perfect. So we're kind of working backwards here, right? We know the formula for the horizontal component, Fx equals F times cosine theta, but this time we're trying to find F, the total force. So let's just rearrange that formula a bit. F equals Fx divided by cosine theta. Now all we have to do is plug in the numbers we know. That's 20 divided by the cosine of 30 degrees. You pop that into a calculator and there's our answer. The total force is about 23.1 newtons. See? This whole process of working backward from a component to find the original vector is something you're going to do all the time in physics. It's a really fundamental skill. Okay, we're almost ready to wrap this up. But before we do, there's one more really neat concept I want to show you. It's a very elegant way to talk about direction in physics, and it's called a unit vector. What's a unit vector? It's actually incredibly simple. It's just a vector that has a length of exactly 1. That's it. Its whole purpose in life is just to point in a direction. It has no real size, it's purely a pointer. And to make things easy, we have special symbols for these pointers. We use E, that's just an eye with a little hat on top, to mean point 1 unit in the positive x direction. And we use J for the y direction. So what this lets us do is write any vector, like our vector A, in a really cool shorthand. We can just say it's AX times E plus AY times J. It's just a clean, efficient way to write down both the size and direction of the components all at once. Phew! Okay, we have covered a ton of stuff. So let's take a second and boil it all down to the absolute key things you need to walk away with. This is your cheat sheet. Right here. To find the horizontal component, you use cosine. For the vertical, you use sine. See how those two go together? They're for breaking things down. Then, to go the other way, to rebuild, you use the Pythagorean theorem to find the magnitude and inverse tangent to find the angle. Notice that beautiful symmetry? 2 tools to take it apart, 2 tools to put it back together. If you can remember these 4 relationships, you've pretty much got 2D vector resolution down. And I'll leave you with one last thing to chew on. Everything we've done today has been in 2 dimensions, just x and y. But what happens when we move into the real world, into 3 dimensions? How do you think these ideas would change if we had a z-axis to worry about? That's where things get really interesting. Thanks for tuning in.